The talk was prepared by myself and my colleagues at Neil, Damika, and Manju. I was a member of the TS for a very long time, and Damika was a member of the team created SL4, and Manju is the QA lead for the OS at Neil. Okay, on the left side, we have the awesome SL4 microkernel. I'm not going to explain more about that because everyone here we knew that. On the right side, it is the vehicle operating system we built at NEO called SkyOSM, which has a strong focus on the dependability, right? There are so many things to build an OS based on SL4, so many things to do. But today, I'm going to talk about something that usually don't get much attention, right? And sharing our experience building the OS based on SL4. First of all, I will give an overall architecture, and then talk about the programming interface and the tooling part, and then describe the comprehensive system monitoring and status monitoring and the test suite. Okay. Yeah. First of all, the essential bits. The OS framework is a classic multi-server design. So it has the process server, network server, device server, file server, and the time service. From their names, you can probably tell what they do. The process server is the critical one, aka the root server. It has all the initial capabilities from the microkernel. And yeah, the servers are properly layered to make sure that they don't have any circular dependency. For example, it's okay for the time server to call process server, but not the other way around. During the early days, we had a small incident. So the file server tries to get time from the time server, but somehow the time server calls some libc functions, which actually tries to open a file on the file system, and then the system hands there, right? And also, the processor is critical, right? And it's responsible for creating processes, managing kernel objects, and also service discovery. For example, if the application wants to talk with network server, it first queries with the process server, say, oh, where can I get the network server? Should the policy allow so, the processor will create a channel between the application and the network server. Yeah. As to the drivers, they are still separate processes, not linked to the the servers. And there's a device server, which is the parent of the other device drivers. And it is also responsible for allocating resources, such as memory mapped I/O, IRQs based on the device tree file to the drivers. And yeah, there's also a driver framework, which has the common methods and the skeleton for different kinds of device classes. So in order to create a driver, basically you just fill the pointer functions you care about, and then you have a driver kind of ready and run. And the other part is the core libraries. They are the interfaces provided by the different servers. So basically, the process server, network server, they all have some interface that are in the core libraries. And they are not POSIX, but they are good enough to build applications directly. So you can just use the libcore layer functions to create applications and create drivers. And they had the complexity of the capability management, the cap transfer, all this is SL4 specific functions in the library. So even if you are not an SL4 expert, you could start building something on it. But eventually, I guess you will be an expert. All right, now with all these bits, we have the resource managers, device drivers, and the program interface that actually you can write application for the operating system. But as we were developing the OS and the libcall interface, the application teams was also doing their development in parallel, and they need a stable interface. The libcall interface, like even for today, they are subject to changes. So we can't tell them, okay, use this one, then we change it the other day. They have to modify their code. That's not a good experience. And we also have like a company-wide application framework, which is cross-platform and it uses third-party libraries and requires the POSIX interface, right? At the beginning of the project, we received a lot of questions like, does this support fault? And how do I do the memory map, like a file-based memory map? How do I send a signal? This kind of questions. At the beginning, I was trying to convince them like, you can actually do the same functionality by calling this libcall function and then this libcall function in this sequence with these parameters. But in the end, we just decided that, okay, we implemented commonly used POSIX APIs just to save us some time. And we think it's probably a right move because the existing muscle library is from the foundation is a good start. And we just implement more Linux syscalls based on, so to provide more POSIX functions. Some of the Linux code can be translated to the libcalls, syscalls directly, but some must be emulated in the user mode. For example, the signal part, it has around 2,500 lines of code for the emulation, and it's no fun debugging it. The POSIX layer took us a lot of effort, but I think it paid off. First, it helps the adoption of the OS by the application team, and we don't get too many POSIX-related questions anymore. Secondly, the third-party libraries used by the framework, application framework or IC framework, are ported to the SCAD-OSIM relatively easily with no or little modifications. And it also opens the door to the wider adoption of the application areas. If your application cares about good performance, actually, you can directly use the libcall layer or specialize the API. For example, you can bypass all the socket layer, talking with the network stack directly, though, to avoid data copy. But reusing the existing software stack is critical in terms of building a product based on it. Now we have the essential component, programming interface, and POSIX layer. How do the end user use it to build their applications? We don't expect that they know how to build the OS from scratch, right? So we provide the SDK as a tool. Basically, it's based on Kernel. So Kernel is used to manage the dependencies. To start writing an application, you just write down the libraries you want to use in the recipe and the version of the libraries. Then the toolkit can compile the application for you, link the correct library, and also download the pre-built binary from the system. And finally, create the image, so you can run the image on QEMU to test your application. That helps application developers a lot because they don't need to know how to build the OS, how to put all the required components together. And as to the system integrators, it helps a lot too, because once you have the right recipe for all the applications you want to use for one car model, right? So you can use that recipe to directly generate the final image for the hardware and run on QEMU or hardware. And this tool also supports the release management, which means that we can reproduce previous build exactly as they were. This helps a lot on the debugging side because sometimes we need to reproduce the bugs in the previous releases. And if we can't reproduce the build, we can't reproduce the bug. With the POSIX layer, we also have like plenty of tools ready for use. There are many toys from the toy box, right? And we also have the SSH from the open source project. But as to the utilities that are closely coupled with underlying implementations, such as PS top or list of files, they have to be implemented from scratch. But we have a lot of tools ready to use. And I can't emphasize enough about the debugging tool side. It at least made my life a lot easier. So we have the kernel tracing level tool, which helps us to understand what the kernel is doing on each call at a certain time. We have the application level tracing to help us understand what an application is doing and how long each syscall takes. And when a server or application crashes, right, so there's automated system to catch the backtrace of the application. So you can use the backtrace for analysis. But maybe you will ask, what if the file system crashes? Any guesses? Okay, if the file system crashes, we save it directly to the raw disk blocks. So you still get the trace of the crash file system. But what if the eMMC driver crashes? And okay, so if the block driver actually crashes, we save the backtrace to the SSH RAM, which is persistent across boot, reboot. So after the system is up and running, we dump the trace from the SSH RAM again. Then we get the backtrace. So we really take this very seriously for the debugging, because yeah. And during the early days, when we have the issue about the file system and the FS, like device block drivers, because the utilities on disk, you can't execute actually any command to do the troubleshooting. So we kind of have to build another tool in memory to minimal system. So if the network is working, you can log into the system from the memory system and debug all the driver and file system related issues. And they do help a lot. Usually a dump of the high-end file system or device drivers, it can help the status of the threads. They can help us to figure out what is happening. Yeah. So in summary, tools are really useful, and we are planning to build more tools for different purposes. Okay, now let's talk about the fuchsia. It's a functional safety. Functional safety is critical for vehicle operating system, and this diagram outlines the hierarchical monitoring we use for the OSM. So the APP manager is responsible for monitoring all the applications. Should they crash, and the APP manager can restart them if needed. And as to the servers, there is a startup verifier, which is responsible to to make sure that the servers are brought up correctly with correct parameters. And when the servers are running, there is another one called the server status monitor. It monitors the status of the servers non-invasively through shared memory. So the server monitor doesn't call to the server, because if the server crashes or fails, the server monitor would be blocked there, right? And it even has its own timer device to avoid calling into timer service for sleep. And there's another APP called Safe Test APP. It actually periodically sends requests to the different servers to say, hey, can you finish this job? And it checks the result of the job. This one, test APP, can be restarted, so you can do the syscall. And if all the monitoring staff, they found any issues there, they will report to the Safe Harbor, which has the final decision about what to do, how to deal with the issue, from a component level restart or from the whole system restart. Right? But what if the Safe Harbor, the fuchsia itself, has some issue? Yeah, we'll try to build this as reliable as we could, but there's the watchdog, hardware watchdog. So if the future is not doesn't pat the watchdog periodically, the system will be resetted should the current condition allows it to do so. So maybe you think, if we have an unverified software stack, do we still need such like elaborated monitoring stuff? Yes or no? Yeah, there are still like hardware faults, so that may affect the software. Yeah, and this kind of elaborated monitoring is required. Okay, this we talk about a lot of formal verification, but yeah, in the real world, the testing is still the mainstream method for ensuring the quality of the OS framework. We have different levels of testings. I think most of you are familiar with like unit test. They are for the function level or syscall level testing. POSIX compliance conformance tests. We borrow the LTP to test the correctness of the POSIX implementation. And the scenario-based testing, so we extract the code patterns from the previous projects to make sure that they are well supported by our code, by our system. Fault injection, we intentionally introduce errors into the system to evaluate the effectiveness of this monitoring we just talked about. And the stress testing, we borrow the stress NG to access the different components of the system, like a virtual memory, file system, or networking. So the stress NG, usually they can make sure all the cores are fully utilized. And yeah, stressing the system significantly with a very high workload. Performance test, okay, we don't need to talk about much about that. Everybody knows that. So for system integration, we put applications and the system together and test them as a whole package. I want to mention that this is only done by the operating system team. The downstream users, they have their own separate tests to run. Yeah. So with all the testing effort, we did solved around 3,000 defects over the past 3 years. There are just so many bugs for the new system, yeah. And fortunately, there are only 2 kernel bugs there, and of course on the verified part. One is on the kernel big log, and the other is on the API. Yeah, so very impressive. So, okay, here are some numbers on the test we have, the scale, the snapshot of test. For each MR request, if you want to merge your code, you have to pass this test. It's around 4,000, which took around 1 hour to finish. So instead of hearing my code is compiling as the excuse, you are hearing my code is passing the pipeline, passing the test. For nightly tests, there are around 6,000 running on hardware and QEMU each day. So it takes around 6 hours to finish. Yeah. For stress tests, there are 400 of them. The runtime are from 1 hour to 12 hours for different kind of stressors and combinations. Performance test, around 200 and 200 minutes to finish. So we hope we could reduce time to 150 minutes by improving the performance further. Conformance test is around 3,000 and takes 70 minutes. And finally, the fault injection, 800 of them. Yeah. So I hope this can give you a feeling about the importance and intensity of the testing when building a real product based on it. Okay, what do we learn? So the first one is building a POC is relatively easy, but making product at least 10 times harder. Yeah, maybe 20. Okay, this project started in 2021, and a small team of 4 members did the initial POC, all the essential component part in around 4 months on QEMU, right? But after that, we spent a lot of time on the POSIX layer, as well as and improving the performance, but at least we spend the equal time on maturing the system. For instance, when we just started, we run the stress NG. A lot of stressors failed immediately after they start. And for those ones that don't start, probably they just hang there. Right? But now we can run the stressors with different combination for many hours without issues. And another example is like for important test scenario, initially the failure rate is around 50%. Sorry, 40%. And now all 1,000 runs of such tests pass. Resource manager is fundamental to the OS, but it's very difficult to get it right. The SL4 is a capability-based system, so we have another kind of resource leakage. It's called sys-space slot leakage. Yeah, apparently it's a bit harder than the memory leakage because you have to remember if you need to delete the cap in the slot before you free the slot. Yeah. And also, when a process terminates, normally or abnormally, the servers have to make sure that they free the resources used by the processes, right? This seems very straightforward, but even for experienced server developers, you can't get it done. They can't get it done the first time correctly. And that's why the multi-server approach and the POSIX don't play well. Yeah, they don't work efficiently. For example, for the file-based map, it needs several IPC to set up the initial setup, and then to handle a page fault, it needs another 2 IPC to do so. And the select and the poll, they need to talk with the different servers to set up the initial setting, right? Not to mention the fork, which is probably the most complex one. And actually, the author of the fork and the exec is Huichao is standing right there. So if you have any questions or you want to hear his complaints, talk with him. He also wrote a lot of tools like the tracing tools and the PS top I mentioned before. So because of him, I have the time to prepare the slides. Yeah. As we mentioned before, the tooling is essential for developers, OS developer productivity. I already gave some examples about how we handle the file system failure, how debug the device drivers, this kind of stuff. So I will skip here. And that's why it's the deliver first. So car has a delivery date, so is the OS. Sometimes we have to make sure that we start development when we have a reasonably good approach for doing something, right? It's a kind of luxury to find the perfect solution, but of course we will keep improving. And also, the lesson is like gain users first. So the users they build the real stuff based on the OS, and they can give you more requirement or feedback. So by solving the user's problem, actually you are improving your OS. This helps a lot. And you can also help the users to tune their application for the OS for better performance. As I mentioned before, they can use the data express path for the high performance networking. And lastly, and most importantly, like stay calm and trust your kernel. Yeah. Okay. And so what we would do differently. The first one is like we would like to shift the functionality on the data, bookkeeping data, okay, of the server to the libraries as much as possible. Because keeping the client data as little as possible on the server side reduces the complexity of the restart server, and it also makes the server simpler, which means probably less bugs, which have like system-wide impacts. And the next one is prefer notification over endpoint for I/O for building IOC calls. We have the issue that when we're injecting the signal to a thread, and if the thread is at the block on reply state, the syscall will be restarted once we contact with switch back to the original thread. And this problem doesn't exist for the notification object. It also enforces you to use the shared memory, so you can use for data, for request and response. So it avoids the message copy, and also it supports the asynchronous I/O just naturally. Support rather early. Okay, so the memory issues are still very common. So we hope that we could support Rust early and started using Rust for some servers from scratch. But yeah. The next one is using Clang as a default cross compiler. It has a better integration with the libc++, and it just compiles much faster. And then a lot of safety compilers are based on the LLVM like architecture, so switching to the safety compiler would be easier. Tackle the complex POSIX API early. Yeah, we should just bite the bullet, and so we can start test application and improving the POSIX API. And the last one is important. Make sure every OS developer watch the AOS course and read the SL4 manual. There are just so many new concepts to digest, so maybe we should even set up a quiz for that. If we make sure that the application the developers get a good understanding of the core concepts, probably we will have less bugs. Okay, finally, make a wishes, or maybe just wild ideas. Yeah. The first one is the page mapping syscall support multi-page in one go. Okay. Yeah, that would save a lot of trips to the kernel. Yeah, trips to the kernel, and also reduce the space bookkeeping overhead somehow. But now with the user mode, we have the shadow page tables. So yeah, and maybe also page table level sharing to avoid duplicating frames one by one. Yeah, and not sure how feasible that is. Maybe German can tell. The verified SMP kernel, and yeah, it looks like I missed the multi-kernel, which is the promising one. So yeah, and we also hope that there will be more real-world application of these systems we can learn from and exchange ideas. And a two-side approach for formally verifying the core components, like if we can write something in a language or in a certain way, so we can get the verification somehow. It was this is not too far away because Pancake is there. All right, I will skip the fun bit, random fun bit, and okay, happy to take any questions.
Thank you, Yanyan. Questions?
So on your wish list was more real-world systems to learn from. Mm-hmm. If I say that your system is a real-world system to learn from, can we learn from it?
Depends on the depth.
Depends on the
sure. I mean, defining learn from first.
I don't know, like you seem to have done like one of the biggest SEL4 based systems around. So you probably learned a lot of lessons, and a lot of them are in there. But
yeah,
is there more? Like, can we get? Like, are you planning to make some parts of it open and release it to people, or document it in some way, or talk more formally about lessons you've learned or design decisions you've made and stuff like that?
Yeah, I'm definitely happy to talk about the design decisions and the mistakes or something we can share about. But as to like publishing the component, maybe Ning could help on that.